In question number 16, amount of charge that will flow through the switch S after it is closed is, see the figure here. Well, we need to find how the charge will be flowing after the switch S will be closed here. So first, what we shall do, we shall just find the effective capacitance and the charge distribution before and after the switch is connected. So this is the simplistic form of the circuit that I have drawn here. This being 4 microfarad, here 6 microfarad, so effective capacitance of these two portions will be 4 into 6 divided by 10, and it's been connected to 5 volt battery, so the charge will be 12 microcoulomb. So here initially 12, and this portion being 12 and 12. So clearly battery has supplied 24 microcoulomb of the charge on this system of capacitance. Now once this switch is closed, now these two capacitors of 4 microfarad and 6 microfarad, these two will be connected in parallel, and the potential difference across these 2 points will be how much? 5 by 2 volt. So the final charge after connection of the switch, it is this being 4 microfarad, so I would say 4 into 5 by 2, so it is 10 microcoulomb of the charge here, and here 6 into 5 by 2, it will be 15 microcoulomb of the charge. Similarly on this side it will be 15, and here it is 10. Looking onto this configuration now, initial charge was 24 microcoulomb, and now it is 10 plus 15, that is 25. So effectively battery must have supplied 1 extra microcoulomb of the charge along this direction. Initial charge was 12 and now it is 10, so 2 microcoulomb charge must have flown along this direction, and this was 12 initially and now it's 15, so definitely here it is 3 microcoulomb. So this direction it is 3 microcoulomb, this direction it is 2 microcoulomb. So along this direction, here 3 and here 2, so definitely along this direction there would be how much? 5 microcoulomb of the charge must have flown across the switch. So looking onto the option for question number 16, 5 microcoulomb of charge from A to B, this is the way the charge must have flown. So option 2 is the correct answer. Now let's proceed to question number 17. A network of resistances, cell and capacitor of C to be equal to 4 microfarad here is shown in the figure. Current in the unknown resistance R in steady state condition is shown. The charge on the capacitor and value of R respectively are. This being 12 volt, this is 0, this is 2, and this is 4 volt. Simply in steady state, this is the way the current will be flowing. I am starting from this point, 12 plus 2 minus, let the current being I, it is I to be given is equal to 2 ampere, it is 2R, and minus 4 is equal to 0. So the value of 10 divided by 2 is equal to R, that's coming out to 5 ohm. Well, if this is the 0 potential, then this will be at the 4 volt. There is no potential difference across the capacitor, so I would say there would not be any charges on the capacitor, and the value of resistance that came out to be 5 ohm. We need to find the charges and the resistance respectively. Option 3 is the correct answer. Got it? In question number 18, electric charge is uniformly distributed along a straight infinitely long wire of radius A. The charge per unit length of the wire is 2 microcoulomb per centimeter. A cylindrical surface of radius 10A and length 0.5 meter symmetrically encloses the wire. The total electric flux passing through the cylindrical surface in SI unit is. It will simply be Q inside by epsilon naught that we must be knowing here. This is the wire, and we need to find the electric flux through this surface, this radius being 10A. So it will simply be phi is equal to Q inside by epsilon naught. Q inside is how much? We need to find the linear charge density first, that is 2 microcoulomb per centimeter, that means in 200 this is 2 microcoulomb per meter. This length is 1 by 2, that is the Q inside, divided by epsilon naught. This is the value of the flux. 2 will cancel out, or it is 100 microcoulomb divided by epsilon naught, or we can say 10 to the power minus 4 divided by epsilon naught is the value of the electric flux. Answer is option 2. That's the correct answer. Now let's proceed to question number 19. Here in question number 19, a charge of 50 nanocoulomb is uniformly distributed over a hemispherical surface of radius 20 cm. Electric field at the center of the hemisphere will nearly be. I am using a very standard answer for this calculation, that is electric field at its center will be sigma divided by 4 epsilon naught. So E would be sigma is Q, that is 50 into 10 to the power minus 9 divided by 2 pi r square. This is 2 pi r square into 4 epsilon naught. 4 pi epsilon naught will be taken as 9 into 10 to the power 9 into 50 into 10 to the power minus 9 divided by 2 r square. Once you make the calculation, it will come out to be, this will cancel out, it is 9 into 25 here, and this is r square. R square is 0.04. So it will come out to be 5.6 into 10 to the power 3 Newton per Coulomb, somewhere around here. So I would say for question number 19, option 3 is the correct answer. Now let's proceed to question number 20. In question number 20, the specific heat S of a solid substance at low temperature varies according to S is equal to AT square, where A is a constant in a SI unit and T is temperature in Kelvin. A piece of this solid of mass m kg is taken and its temperature is raised from 10 Kelvin to 30 Kelvin. The amount of heat required in this process in SI unit is. Small amount of heat that will be required once the change in temperature happens to be delta T. It will be m specific heat into dt, specific heat being how much? A T square into dt. Just integrate this portion, we shall have the complete answer. So Q is equal to ma, it is TQ divided by 3, it is from 10 to 30. Q is equal to 26000 divided by 3 into ma. This is our final answer for question number 20. Option 3 is the correct answer.